Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. Imagine yourself standing alone on the Martian surface. The ground beneath your boots crunches with a sound like dry sand, but sharper, harsher, as if the planet itself resents your presence. Above you, a sunburnt sky stretches vast and empty, the thin atmosphere barely scattering the sunlight into a ghostly salmon hue. The air pressure here is less than 1% of Earth's, meaning if you took off your helmet, your blood would quite literally start to boil. Not from heat, but from the sheer absence of pressure. The temperature around you bites with a deadly chill, dipping to minus 70 degrees Celsius as the red horizon shivers under a blanket of freezing winds. This is a world that has been dead for billions of years. No forests, no rivers, no soft whisper of leaves in the breeze, just silence, eternal and absolute. Now dare to imagine something impossible, life taking root here. Not in decades, not in centuries, but beginning now, with something so small you couldn't see it with the naked eye. A life form that asks for no shelter, no protection, only sunlight, carbon dioxide, and the stubborn will to survive. What if the first great terraformers of Mars aren't towering machines or brave astronauts in high-tech suits, but tiny, genetically engineered algae, whispering the first breaths of life back into a dying world? You might think algae are simple, maybe even boring, but in reality they are some of Earth's oldest and most important survivors. Over 3.5 billion years ago, long before trees, before dinosaurs, before anything walked on land, algae were busy transforming Earth's atmosphere. Through photosynthesis, they exhaled oxygen and inhaled carbon dioxide, slowly tipping the balance of gases in favor of life. Without algae, there would be no ozone layer shielding us from deadly radiation, no lush rainforests breathing life into the air, and no humans gazing at the stars, dreaming of other worlds. Today, algae thrive in places so extreme they almost seem alien already. In Antarctica, there are red watermelon algae that bloom on the snow, surviving in temperatures of minus 20 degrees Celsius. In the Sahara Desert, tough cyanobacteria endure searing heat and parched winds by hiding beneath rocks. Near volcanic vents, algae cling to rocks, bathing in boiling acidic waters that would kill most other forms of life in seconds. These tiny organisms are masters of adaptation, nature's original bioengineers. Now, picture this resilience. Turn toward Mars. Its atmosphere is over 95% carbon dioxide, with a surface pressure less than 7 millibars, about 600 times thinner than Earth's. Radiation from cosmic rays and solar storms bombards the ground daily, unchecked by a magnetic field. Temperatures swing wildly, often between minus 60 degrees Celsius at night to a warm 20 degrees Celsius near the equator by midday. And yet hidden beneath this bleak exterior are possibilities. Frozen water exists at the poles and in underground reserves. Sunlight, though weak, still reaches the surface. Mars, for all its hostility, isn't entirely dead. It's sleeping. Dream is bold. Engineer algae capable of awakening Mars from its long slumber. Synthetic biology, the art of redesigning life itself, is advancing at breathtaking speed. In laboratories around the world, researchers have already created algae strains that photosynthesize more efficiently, withstand extreme salinity, tolerate higher radiation levels, and even produce useful compounds like biofuels and vaccines. This same technology could be used to tweak algae to survive on Mars, maybe even thrive. These superalgae could serve several critical roles. First, they would absorb Mars's abundant carbon dioxide and release oxygen as a byproduct of photosynthesis. Over time, as more oxygen builds up, it could thicken the atmosphere, however slightly, and protect future settlers from the deadly thin air. Second, some genetically modified algae could be designed to secrete dark pigments or minerals onto the surface, lowering Mars's high albedo and allowing the planet to absorb more heat from the sun, warming it just enough to support liquid water at the surface. Third, the algae could prepare the soil, slowly enriching it with organic matter, setting the stage for higher plants, mosses, and eventually entire ecosystems. Experiments have already scratched the surface of this idea. In a landmark study at The German Aerospace Center, researchers exposed cyanobacteria to a Mars-like environment, a mix of low pressure, high carbon dioxide, freezing cold, and intense ultraviolet radiation. Amazingly, these hardy microbes not only survived, but continued to grow and photosynthesize, producing measurable amounts of oxygen. They used just basic minerals, a trickle of water, and the faint light of simulated Martian sun. If life can cling to existence under those conditions in a lab, could it eventually flourish on Mars itself? There are even bolder ideas. Some scientists propose creating biodomes or bioskins, sealed, nutrient-rich habitats seeded with genetically modified algae, designed to slowly spread outward and terraform small areas at first. Others imagine scattering spores across the planet from orbit, letting evolution take over, mutating and adapting algae into even more extreme survivors over time. It would be slow, perhaps painfully slow, taking centuries or millennia, but it would be real. A patient biological transformation, inch by inch, breath by breath. Of course, with such revolutionary potential comes immense responsibility. What if native Martian life, primitive, hidden deep underground, still exists? Introducing Earth organisms could destroy it forever. What if engineered algae mutate unexpectedly, creating harmful or uncontrollable ecosystems? Scientists are grappling with these ethical dilemmas even now, weighing the incredible promise of terraforming against the risk of playing God on another world. Still, one truth remains. Every great journey starts with a few brave explorers. Right now, Cosmics. Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. Now that we've envisioned the raw possibility of transforming Mars with the tiniest seeds of life, let's journey deeper. In the next section, we'll dive into the cutting-edge world of genetic engineering, how scientists could reprogram algae at the molecular level to endure the brutal realities of Mars and reshape an entire planet one cell at a time. The journey from dream to reality always begins with a blueprint, and when it comes to terraforming Mars with algae, that blueprint lies not in machines or monuments, but in the very building blocks of life itself, DNA. Imagine a single strand of DNA, thinner than a spider's silk, yet packed with the instructions for survival, growth, adaptation, and now, thanks to human ingenuity, perhaps even planetary transformation. But how exactly would we take algae, already hardy and adaptable, and make them even stronger, smarter, and more Martian-ready than nature ever intended? The answer lies in the cutting-edge science of genetic engineering. Over the last few decades, researchers have learned to edit life itself with tools so precise they seem almost magical. The star among these tools is CRISPR, short for clustered, regularly interspaced short palindromic repeats, a revolutionary technology that acts like molecular scissors, allowing scientists to snip out unwanted genes and insert new ones with astonishing accuracy. With CRISPR and other advanced techniques, we can now reprogram organisms at the genetic level, tweaking, enhancing, and reshaping their abilities in ways evolution alone could never achieve. But reprogramming algae for Mars is not as simple as flipping a switch. Mars throws down a gauntlet of brutal challenges, each demanding specific biological upgrades. First, the temperature. At an average of -60 degrees Celsius, ordinary algae would freeze solid. To combat this, scientists are looking at genes from cryophilic or cold-loving algae found in Antarctica and the Arctic. These organisms produce special proteins called anti-freeze proteins, which prevent ice crystals from forming inside their cells, essentially allowing them to survive where most life would be shattered by cold. By introducing these anti-freeze genes into our Martian algae, we could create strains capable of photosynthesizing, even as ice frosts the ground around them. Next comes the issue of radiation. On Mars, without a protective magnetic field, cosmic rays and ultraviolet radiation bombard the surface relentlessly. On Earth, algae living high in the Andes Mountains and in polar deserts have evolved thick pigmented cell walls packed with protective compounds like carotenoids and cytinamin, natural sunscreens that shield their delicate inner workings. By enhancing these pathways, or by splicing in even more robust radiation resistance genes from extremophiles like Deinococcus radiodurans, sometimes called the world's toughest bacterium, scientists could armor Martian algae against levels of radiation that would be instantly lethal to us. Then there's the thin atmosphere and low pressure. Terrestrial algae are accustomed to Earth's lush blanket of atmospheric gases, but on Mars, gas exchange becomes a desperate struggle. Some algae, particularly certain cyanobacteria, have evolved to function under very low oxygen levels by tweaking their metabolic pathways and creating specialized cells called heterocysts, which shield sensitive reactions from the outside world. Genetic engineering could push these adaptations even further, optimizing photosynthetic machinery to function in conditions barely above the vacuum of space. Water scarcity presents another brutal hurdle. Mars today has water, vast amounts frozen at the poles or locked in subterranean ice, but liquid water on the surface is fleeting, transient, and often laced with toxic salts called perchlorates. To survive this, Martian algae would need desiccation tolerance, the ability to dry out almost completely and then revive when moisture returns. On Earth, desert cyanobacteria perform this miracle regularly, entering a state of suspended animation. During droughts, only to burst back into life with the first drop of rain. Researchers could harness these genes, perhaps even enhance them, allowing Martian algae to ride out long dry spells, reawakening with every melt, every seep, every tiny droplet. Beyond these survival traits, some visionary scientists propose engineering additional terraforming functions into Martian algae. For example, producing methane, a greenhouse gas far more potent than carbon dioxide, to slowly thicken the atmosphere and trap more heat. Certain Earth microbes already produce methane as a byproduct of their metabolism. If similar capabilities were spliced into algae, Mars might begin to warm itself, triggering a cascade of climate changes that could eventually support more complex life forms. There are even ideas to make algae self-repairing, resilient to genetic mutations, and capable of adaptive evolution, so that once seeded on Mars they could evolve independently, growing stronger with each generation, better suited to the red planet with every passing year. Yet, while the promise is dazzling, the challenges loom just as large. Every tweak to the genome carries risks. Changes that seem beneficial in the lab could spiral out of control on the open surface of Mars. An algae strain designed to darken the planet and warm it might overgrow, covering vast areas but releasing toxic byproducts. Worse, mutations driven by cosmic radiation could create unforeseen side effects, hyper-resilient strains that no longer serve our goals, or even ones that threaten future human habitats. And beyond practical concerns lie the moral ones. When we alter life so profoundly, are we still working within the boundaries of nature, or crossing lines that shouldn't be crossed? If we unleash engineered organisms on another planet, do we risk contaminating an environment that might hold its own ancient secrets, still buried deep beneath the Martian crust? Still, humanity has always reached beyond what was deemed safe or easy. The first people to cross oceans, to climb mountains, to set foot on the moon, they all faced unknowns, risks, and doubts. If we choose to terraform Mars, to cradle life on a new world, it will be the most audacious chapter of this ancient human story. And perhaps billions of years from now, if Mars becomes a living world once more, it will all have started with a few tiny cells, a handful of brave, engineered algae whispering the first fragile breaths of life into the ancient silent winds. The day will come when all the genetic engineering, all the lab experiments, and all the theoretical models will face the ultimate test: Mars itself. But seeding life on another planet isn't as simple as tossing a handful of algae into the wind and hoping for the best. It will require careful planning, ingenious technology, and a deep understanding of Mars's complex and hostile environment. In this section, we journey into the strategies scientists are dreaming up, and some are already building, to deploy these microscopic pioneers across the red planet. First, imagine the very beginning, a small, sleek lander descending through Mars's thin atmosphere, its heat shield glowing as it punches through layers of pink dust and ultraviolet light. This isn't a spacecraft carrying astronauts or rovers searching for fossils. Instead, it carries something far more delicate and profound, a precious cargo of genetically engineered algae kept in suspended animation, waiting for the right moment to awaken and begin its silent work. Scientists envision small-scale pilot missions like this, where contained, carefully monitored algae farms would be set up under transparent domes or inside specialized bioreactors. These first tests would serve multiple purposes. They would allow scientists to monitor the algae's survival in real Martian conditions, testing whether the cold, the radiation, and the extreme dryness are truly within engineered tolerance limits. They would also let researchers fine-tune environmental factors, adjusting soil chemistry, testing different energy inputs like sunlight or artificial lamps, and ensuring that the algae can perform their photosynthesis efficiently even under Mars's weak solar rays. If these pilot tests succeed, the next step would be to go bigger. Some researchers propose creating larger bioblankets, thin, flexible sheets seeded with algae spores and nutrients, designed to be unrolled over vast stretches of the Martian surface. These blankets could trap heat, retain small pockets of moisture, and protect the algae during their most vulnerable early stages of growth. Over time, the algae could spread naturally, expanding their colonies as microhabitats slowly emerge from the barren dust. Others imagine using drones or autonomous rovers to spread spores directly across promising regions, especially near the polar ice caps, where seasonal melting provides a rare, precious source of liquid water. These robotic gardeners would scout for ideal microclimates, sheltered craters, canyon floors, or regions with buried ice. As technology advances, these drones might even evolve into fully automated terraforming units capable of repairing damaged colonies, dispersing nutrients, and monitoring oxygen production in real time. Yet perhaps the boldest idea of all is to seed Mars from orbit. Picture a future spacecraft releasing a fleet of microscopic capsules, each one carrying resilient engineered algae, designed to survive the plunge through the atmosphere and scatter across the surface. This shotgun approach, sometimes called panspermia seeding, would maximize coverage, letting natural selection and local conditions determine which strains survive and where they thrive. It would be a biological gamble on an epic scale, but if successful, it could jumpstart the slow planet-wide transformation we seek. One particularly fascinating area of focus is targeting regions with natural geothermal activity. Mars, though, largely geologically inactive today, still has pockets of heat lurking underground. Certain areas show evidence of recent volcanic activity, no more than a few million years old, practically yesterday in planetary terms. Warmth from these regions could provide microclimates just a few degrees above the lethal cold, enough to give engineered algae an edge. Some scientists dream of terraforming hotspots, where life could first gain a real foothold before radiating outward into the colder regions beyond. However, seeding life on Mars is not just about logistics. It is also a deep, profound gamble, with ecological consequences. One major concern is planetary protection, the principle that we must not contaminate alien worlds with Earth life before we have thoroughly searched for native life. What if, buried beneath the dusty plains or hidden inside the subsurface ice, ancient Martian microbes still exist? Introducing aggressive engineered algae could wipe them out forever, erasing a biological lineage billions of years old before we even know it existed. To navigate these ethical dilemmas, organizations like NASA and the European Space Agency, alongside independent researchers, are already drafting complex planetary protection protocols. Some propose strict containment for early experiments, ensuring no biological material escapes until we are certain no indigenous life remains. Others advocate for a phased approach, starting with the harshest, most sterile regions, places where the odds of native life are almost zero, and only expanding to more hospitable areas after decades of study. Still, the temptation is powerful. Mars is tantalizingly close, only months away with current technology, and its silent plains seem to cry out for life, for warmth, for the green breath of photosynthesis. For every voice cautioning patience, another calls out for boldness, for the incredible dream of transforming a dead world into a living one. And beyond Mars, the implications are even grander. If we master the art of seeding life across planets, what limits remain? Could we someday breathe new life into Europa's buried oceans, or Titan's frozen shores? Could we become gardeners of the solar system, and one day the galaxy itself? But first, it all begins with algae. With tiny, fragile spores drifting across alien sands, with patient generations quietly weaving a new atmosphere from sunlight and stone. After all the dazzling possibilities, the technical marvels, and the breathtaking risks of terraforming Mars with genetically engineered algae, we are left with one last question. Should we do it? Should we take the leap and attempt to breathe life into a world that's been silent for billions of years? Can we really bear the responsibility of reshaping an entire planet, knowing that the consequences of our actions could echo across centuries? As we stand on the precipice of space exploration, the debate is more than just a matter of scientific curiosity. It's a philosophical and ethical challenge that cuts to the heart of who we are as a species. For all the excitement about making Mars into a second Earth, there are deeper questions to consider. Are we prepared for the ecological consequences of our actions? What happens if the algae run wild and become something we never intended? Could we accidentally unleash a new form of life, one that escapes our control and transforms the Martian landscape in ways we never imagined? Or perhaps, in our efforts to make Mars hospitable to humans, we are forgetting the most basic rule of exploration. We must tread lightly, for we are intruders on a world that may already be unique and precious in ways we cannot fully understand. The ethical dilemma of terraforming is not new. It's a debate that has existed for centuries, ever since humans began altering the Earth to suit our needs. We've reshaped ecosystems, paved over forests, and changed the very climate of our planet in pursuit of progress. But Mars is different. Mars has not yet been touched by human hands. It is a pristine, ancient world, one that has existed for nearly 4.5 billion years, far longer than Earth. In the search for life, we have never found definitive proof of Martian life. But what if we're wrong? What if there's something beneath the frozen soil or deep in the cave systems, a vestige of life that once flourished or still struggles to survive in the harsh conditions? If we introduce Earth life, no matter how well-intentioned, could we be committing an irreversible crime against whatever history Mars might hold? For now, we have no answer. But there are those who argue that humanity's future is intrinsically tied to the colonization of other worlds. Mars is within reach. We have the technology, the vision, and the potential to turn it into a new cradle for civilization, a backup for humanity if Earth ever becomes inhospitable. Proponents of Mars terraforming believe that it's not just an opportunity, but a responsibility. With the growing pressures of climate change, resource depletion, and overpopulation, creating a self-sustaining colony on Mars could offer humanity a new beginning, a chance to write a fresh chapter in the story of life on Earth. But there's another layer to this debate, one that asks whether we truly understand what it means to transform a world. It's easy to romanticize the idea of making Mars lush and green, but do we fully grasp the complexity of life? Can we truly replicate the intricate balance of Earth's ecosystems with its oceans, forests, and diverse species? The process of terraforming is not as simple as turning a switch. It is a gradual, unpredictable journey, one fraught with uncertainty. If the algae succeed in transforming the atmosphere, will they also create conditions that support plant and animal life? Or will we find ourselves trapped in a world where only our engineered species can survive? It's a humbling thought, and yet it's also a thrilling one, because in the end the terraforming of Mars is not just about technology, it's about imagination. It's about thinking beyond our current limits, dreaming of a future where humanity has spread its roots to other worlds. It's about the incredible idea that we too can become creators, shaping planets, transforming ecosystems, and perhaps even giving birth to new forms of life. In that sense, terraforming Mars with genetically engineered algae could be the start of something far greater than we can even imagine, a new era of cosmic gardening. But we cannot take this journey lightly. The question isn't just whether we can terraform Mars, it's whether we should. Are we ready to shoulder the consequences of such power? Can we balance our desire to explore and expand with the wisdom to protect what we find? These are the questions that future generations will have to answer as they look back on our efforts with the benefit of hindsight. And perhaps, one day, if Mars is truly transformed, we will look up at the night sky and see a green world glimmering in the distance, a world that we helped create, but also a world that will forever belong to its own history. As you ponder this, think about the path ahead. Humanity's reach has always exceeded its grasp, from the first steps onto the moon to the ambitions that now drive us toward Mars. Could this be the next giant leap? Should we terraform Mars, or should we leave it to its quiet, frozen beauty? The future of Mars is in our hands, but it's also in the hands of those who will come after us, who will continue the work we began, for better or worse. So, what do you think? Should we continue down the path of terraforming, or is there a better way forward? Let me know your thoughts in the comments below, because this journey, like all great explorations, isn't just about one person's vision. It's about all of us together, deciding where we go next. Don't forget to share this video with your fellow space enthusiasts and spread the conversation. We've just begun to scratch the surface of what humanity can achieve in space. Thank you for joining me on this cosmic journey. The story of Mars and our place in it is far from over, and neither is our exploration of the mysteries of the universe. Keep dreaming, keep questioning, and as always, keep whispering the secrets of the cosmos.